Good morning, everybody. So thank you so much for joining us today. This webinar is part of the 3D Printing Housing Hack organized by LafargeHolcim with its partners. Today, you will see an inspiring talk which aims to open up your creativity. After this talk, we will have a Q&A session with the speaker. As you can see, there is a chat on the right-hand side, so do not hesitate to post your questions during the session, and our speakers will answer them at the end. Now I'll hand over to Mihaela from LafargeHolcim, who will give you a bit of context and introduce the rationale behind the event.
Thank you very much, Sam. Hello, everyone, and happy you joined the inspirational webinar for the 3D Printing Housing Hack. So as we all know, the construction industry lacks of productivity, and at LafargeHolcim, we consider concrete 3D printing as an opportunity to revolutionize construction, to make it more sustainable by saving materials, but also to improve the efficiency in construction. So that's why we decided to organize this hackathon, and we really hope to have your brilliant ideas on the topic. So as you know, this is a multi-step competition which aims to revisit housing design with 3D printing technology, and that will combine conceptual design but also prototyping. So before starting really to work on the topic, we propose you this webinar as part of the first phase, which aims to inspire you and to give you insights in order to push the boundaries of your creativity and to have your innovative ideas. So these webinars are made by industry experts, and today we have the chance to have Tim from 20 Additive Manufacturing, which will speak about how to 3D print a house, what are the challenges and the considerations to take into account. Tim, the floor is yours.
Thanks a lot, Mihaela. Thanks, Sam. Thanks for having us here and the opportunity to present one of our projects that we realized this year in Canada. So yeah, I'm gonna present our achievements, and I'm also gonna talk about the challenges that were included, and hope that the participants in this hackathon will be able to develop ideas and be inspired to develop the whole process and bring it to a new level. We're just at the beginning. We're at the beginning of something really interesting and amazing. So I'm gonna present us a little bit. We're 20 Additive Manufacturing. We have our head office in the Netherlands, but we're spread all over the globe a little bit. So I'm based in a prototyping lab in the south of Germany. We have our new big prototyping facility in Western Canada. This comes organically because most of our team members are Canadian. So that's how it went. What we do, we focus on machine development and the whole 3D printing process, not only machine development, but also software that is needed to run the printers, to control the process, to understand the process of 3D printing with concrete or better mortars. We help with the slicing, for example, or design of 3D printed elements, and we also do print on demand. In this slide, you see some of the printers that we are operating. On the left, this is here the prototyping lab based on a small 6-axis robot. In the middle, you can see a Cartesian style printer that also has its advantages. And on the right side, you see our big prototyping printer in Canada, which is basically a mixture. It's a gantry with a robot on top. So the robot is on a 10-meter track and can move up 5 meters. And the amazing part about this printer is it also can rotate around its longitudinal axis, which gives it a quite impressive build volume, which is basically also the difference in those printers. So as we're designing machines and also designing printed parts, we set out to create something, a house, because everybody is asking about houses. Everybody wants to print houses nowadays. And we set out to do something where we could really use the virtues of 3D printing, meaning rectangular buildings are not as interesting as they can be manufactured with traditional methods in a relatively effective way. So we set out to print something that is curved. And in this case, we set out to print something that is curved only. So we designed a house following the Fibonacci spiral based on the Fibonacci sequence. And this is an initial rendering of the house. Relatively small, it's a tiny home with a living surface on the ground floor of 28 square meters. And a small mezzanine here on the, where's my mouse? Here you can see a small mezzanine on the kind of second floor. We were using this Fibonacci sequence as it is, as you can often find it in nature. It's everywhere and it looks really appealing. And it perfectly incorporates the advantages that can be achieved through the process of 3D printing in architecture. Here you just see some examples of the Fibonacci spiral in snails, plants, and arrangement of seeds here at the sunflower. This was the initial steps. We set out to print a building, and now I'm gonna guide you through what we had to do to make it happen. So first of all, we are partnering up with different material suppliers that are specialists and have developed great 3D printing mortars to date. This is one thing to consider. What is the material actually doing that we're printing with? Then there's a whole subject of building physics. So the building has to, of course, withstand the forces of environment and has to be a livable place. In the end, you still wanna be in it. Then the structural system to make it stand. And this is, of course, a big subject because there are quite some regulations are still missing in this subject. And so we were happy to find local partners that helped us incorporate a structural system that was following the rules of the local code. Then we had to consider the available printers. Of course, this is a great problem we have because we have a couple of printers available, which are basically all offsite printers. Right now, we're working on other solutions where we bring the printer to site, or at least close to site. And then there's the whole part of geometry creation or slicing, or there's a lot to it to make a house printable. And then the printing parameters and the logistics. So for the print materials, we basically used two printing mortars. We used a 1K material and a 2K material. On the right, you can see some examples that were built with the two systems. The 1K materials are a little slower in cure time. They allow less overhang in printing and slower build rates, and are therefore a little better for bigger structures because the pass-over time is extended. So that means when we're using 3D printing with extrusion, we're putting layer on layer on layer, and we have to guarantee or to make sure that we have a good adhesion between the layers. So a longer pass over time on those bigger items is needed. And we also wanted to incorporate 2K material because it's quite fun to print it with it, to be honest. You can make intricate forms and fast build rates. It's whenever we see new people in our shop, it's the kid in the candy shop. Their eyes open up, and it's really fascinating. Still, after doing so many prints for us, it's great, and it's fun to see, and you see the potential with it. So the building physics that we had to consider is we had to create an insulating, or like a hull of the building that is insulating enough to bring a good living climate on the inside. This also means that you cannot have condensation, especially not in the walls. And we wanted to avoid thermal bridging as much as possible. So to do that, we had incorporated a hollow wall system that is filled with polyurethane foam after assembly. We decoupled all the load-bearing elements from the non-load-bearing elements, increasing also the efficiency of the wall and decreasing the thermal bridging. This is something you can see here, relatively small, those load-bearing columns. Actually, when you look at this picture here, you can see those load-bearing elements that will later hold the roof structure. And then these are the that are placed on here. And then there is this odd column that is basically not a load-bearing column, but is just used for holding conduit and electrical lines. Yeah, so I already was a little fast on the structural system, but here you can see how we were working together with the structural engineers to build a system that is printable. As mentioned, we were incorporating a system of columns and shear walls. So here, this last element of the spiral is basically fully filled with reinforced concrete to hold horizontal loads. And yeah, here you can see a side view. The patio is actually quite high. It's 4.5 meter high columns in the front that are based of sections. So we split the whole system in 2 layers. Here you can see a little bit the printers in motion. On the right is the printer that we use for most of the prints. It really shows how big it is. It's hard to believe when you're not standing in front of it, but it's a 10-meter long structure, 5 meters high. So basically our whole factory is, or half of the factory is filled with this printer. It has a humongous build volume. In the center, you see another printer that we're operating in Canada, a small gantry printer that we used for printing the formwork for the foundation, which is another thing that we printed. And yeah, this leads to the question, why using different styles of printers? In this case, we were using horizontal elements, so the ground floor up to here was printed in horizontal layers, so sliced horizontally, 1 speed, 1 flow rate, relatively easy. can be done with a gantry-style printer and easy controls. Here on the left, you can see one of the top section elements, which is more difficult to print. The top section is following the roof slope and of course is not rectangular, it is all curved. So we're basically out of two planes. And this leads to relatively difficult slicing. And when the difficult slicing is over, then the difficult machine controls begin, which is not so difficult for us, but it had to be figured out. So here in these areas, the layer height is different to the front. And with the mortar pumps that we're using that are almost standard plastering pumps, they're modified to be incorporated in the control setup, so we can start and stop them remotely with the G-code commands or robot commands. So the flow rate is fixed. In order to have a consistent bead width and bead geometry of the prints, the speed can be modulated with the robot, as well as the tool orientation. The tool orientation here is following perpendicular to the non-planar layers. Here another showcase of non-horizontal printing with 2K materials. In the house itself, we didn't use as extreme overhangs as here, as we were using the 1K material, but yeah, just to show you guys what is possible maybe. We were lucky enough to print this building very close to our printing facility, so we had only 50 meters to transport, but it was basically showing the whole process of printing offsite. Just the distance was a little less. This means we have all the pros with it. We have a controlled environment, which is very essential so far because the printing process is relatively sensitive when it comes to changes in the climate that you're printing in, when it comes to changes in temperature, humidity. Also, the temperature of the building materials is very essential to have a consistent print. The cons are on hand. It is that we're not printing this whole structure in one shot. We had to split it up into different printable segments, and all those segments had to be cured in place before they could be transported and joined after assembly. Here you can see how full the shop was at some point. So we were basically printing, filling up the whole shop, and then we could start transporting the first ones. And then we were rotating. In all, we printed this house out of 20 different components that were split, of course, into printable sections, and then other considerations had to be taken to split the items into transportable sections, which was basically in the end the bottleneck. We had to consider the crane capacity that we were using to move the parts in place after they were printed. It's actually very tricky to print something that is so big you cannot transport it anymore. Have to watch out for that. So yeah, but we had an algorithm with it that was basically first splitting the house into sections that were light enough to be transportable. And we had to consider an assembly strategy and also had to consider how to lift those items. They're not light at all, so we were printing parts that were weighing up to 2.5 tons, so no way to move them manually somewhere. That means we had to incorporate lifting points, and we were relatively conservative, because also for us these were the biggest parts that we were transporting in the beginning. So probably had more lifting points than needed, but everything went well. Here you can see another topic that we had to address. It is basically we were splitting the house in 20 different pieces, and then for having a continuous print path, we were joining them back together in groups that would fit the build volume. This had advantages and disadvantages. So the idea was to cut them while they were green and having them split again, because later you will see the post-processing can also be a little, can be time consuming and can be not so fun. Another thing you can see here is how we split the house into the levels and put the split line exactly where the windows are. Here on the right side, you see one of our preliminary tests where we put a temporary structure in the window opening and print it over top, which works okay too. So yeah, more details about the geometry creations. Precision of the prints, of course, is something to consider, and then for assembly, the tolerances and gaps had to be met. So is the printed element really as spec'd? How wide is our bead? Does it really come together as planned, basically? So this came with a lot of challenges and a lot of new insights for us. When it comes to assembly, post-processing, and the whole process itself. As our structure is not rectangular, there's quite a challenge in measuring in all those parts. So this is where we're working on right now, to be placing those parts with AR so that you're fully incorporating the digital workflow. This was basically the only moment in the build that we had to print something on paper. When we were, of course, when we had to hand in documentation for the permission, but when we were measuring in the parts, we had to create many measuring points to properly set each element where it needs to be. And there is definitely room for improvement. Here, other fun tests that came before we started printing the house itself. On the left side, you see a video of one of our ideas of reducing thermal bridging while still incorporating, I'll just play it again, while still incorporating a kind of a lattice structure of a wall section. So this could be the inside or the outside shell of a wall. And then we were here. This is actually a Gothic arch that we're printing on the inside, and this is a diamond shape to reduce the area of touching of the lattice structure in the inside. This is a process that is possible with the 2K material, which we finally didn't use for the outside walls itself. Here you can see iterations on the incorporation of our load-bearing columns. So with this printing system, there's always a challenge of doing start-stops, which is basically possible, but affecting the surface quality a little bit. It's more like an optical thing that is disturbed. So often there's a little blotch or a little blob of material that is not completely smooth. as you would want to have it. So we decided on using techniques that are continuous. And yeah, on the right side, you can see some iterations to figure out what looked best. Here, it's the printer is following a loop and going up and down and coming back, so making a continuous print path. Here, it's the same thing, just with different offsets and different inclinations and angles, how the walls would lead into the column section. Same thing here, but just inverted to not have the column visible, but still have the thermal separation between column and outside wall. And this is what it finally became. Actually, this is another iteration where we were still too close to the outside shell and didn't have enough insulation on the backside of the column. And we just moved the column further inwards. You will see later in the printed pictures how it looks. So the columns are completely visible, but as I think, in a nice way, actually. Second here. Okay, now it works again. Here's a bigger picture of the wall connectors that we were testing in the beginning. So, as well as the zigzag walls, as we call them, or some lattice structure. And here also another system where walls are just partially connected. Unfortunately, this would be very beneficial for the building physics, but is only possible with the 2K materials. Other considerations were how to include electricity, water lines in the building, which is partly easy because we have hollow walls. So we have already cavities that don't have to be put after the fact, except the holes that had to be placed in the walls. And this is something that, maybe this hackathon will spark some better ideas on doing this, because after drilling a couple of those wall outlets, it became less fun, to be honest. And a lot of tests on the non-planar printing. Here you can see how the joint walls actually were printed together. You can see in the central section here, this is an area that we cut out in green state. Another thing that we did, we printed all the wall ends of the wall elements closed. This had different reasons. So we could have left them open with a different printing strategy. But for us, it was a consideration, or actually, let's start over. Ideally, those walls would be open so the insulation could touch each other without interruption and don't have the thermal bridge in the center of the joint of the walls, which we did later. We cut all those printed elements open while we were very close to site. For us, it was a comfort, like we wanted to be in the comfort zone while transporting the elements. Later on, it turned out that this was not necessary. So there's a lot of improvement on the post-processing that was necessary due to the initial thoughts that we had to close the ends off to make those pieces transportable. And yeah, all the different printing parameters that have to be considered, not only geometry of the elements itself, but the bead size itself, which is changeable through nozzle shape, flow rate, and print speed. Then we had to take into account buildability. First of all, the material has to be able to stack on top of each other and has to be able to hold the load of the upper layers. There are methods, for example, from Witteveen and Bose, for predicting those failures. We had to go through trial and error, so we found out the build rates that we can comfortably build with. And as previously mentioned, there are the other factors like the humidity and ambient temperature, the temperature of the water and the material itself, the pumping system, which is something we didn't think about before because we did many test prints but never printed for a really long time. So after using those pumps for hours and hours and hours, they start to clog at areas where there's less flow in 90-degree angles, or all kind of places, to be honest. So we were printing 4 hours in one shot, and then we were taking apart the complete pump, cleaning it, and then you continue printing. And you have to take care of the changing parameters during printing. So opening a garage door is not so great when it's really cold outside. The water content of the mix has to be extremely constant. This is something we test before and after printing. So we do a microwave test, which is fairly easy. And the whole consistency of the process is still a very big subject. I think we're good at most of it, but there's definitely room for improvement. Here's some pictures from the logistics included in the process. Lifting the elements, none of those elements some were easy to lift because there were some straight ones that had the center of gravity really close to normal, to predictable, and then all of the other parts had center of gravities that were more challenging, so we had to lift them on multiple points to lift them straight and also to position them in a way that was easy. Here you can see we're placing first the first half on the bottom and then all the top parts on top. So some facts and numbers. This is maybe taking some questions there ahead. We printed 200 different parts with a print surface of 130 square meters, which is not much material. It's only 6.5 cubic meters of printed mortar, and we printed in 11 days. And we printed in 11 days a little spread out, to be honest. So it was not 11 consecutive days that we were printing. There were a lot of things that were also going on at the same time. Here, please don't take this number for granted. This is a fun spacer number that I put in the presentation before I put the real one in. Okay, and the infilled mortar, or actually concrete, is 1.75 cubic meters, and which was also a little challenging in the beginning because our structural engineer was putting emphasis on that we had to compact the material in the columns. And we got a little scared about that because we had done previous tests where we exploded some of the formwork that we were printing because we were vibrating inside. So it took us a little time to be able to use the self-compacting mortar or concrete for the filling of the structural elements. Thanks God it was possible in the end. It would have been really a lot of sweat for us. Here you can see where it is right now. Actually, it's a little further already. The contractors are actually still working on putting in windows, and the roof is finished now, as you can see here in this picture. The columns in the front are assembled 4.5 meters high. Unfortunately, nobody's standing there, but it looks quite impressive when you're standing next to them. And we're extremely lucky and happy that we could print this house in this wonderful scenery here in Western Canada. It's this stunning view over the Kootenay Lake. Here are some pictures of the challenges that we're facing that I've previously mentioned, some of them. So collapses. I think everybody who's been working with 3D printing concrete has seen this, and it is painful at times after a lot of effort. And then you have a collapse of a part and have to cope with it. We cope with it in different ways. Sometimes we were able to cut it clean and reprint some of the sections, or we had to start all over again. This mainly happened when we were not conservative with the build rates that we were calculating. So for every part that we print, we have an algorithm that calculates the print time and also the build rate. And with that, we can adjust the print speed to meet the build rate needed. Then another thing that was more or less great was cutting of cured printed elements. Here you can see how we cut open the ends of the wall sections to have one thermal hull that is not interrupted. And this was not fun. And of course, sometimes you're fighting inconsistency of the printing itself, some not good looking prints that you can see here. This can have so many variances, and this also has a big room for improvement. So what to improve? Definitely, this is the great thing that we're looking forward to see from you guys at the hackathon, and thanks a lot for inspiring this to the heart. So how to use the least material possible, how to insulate the houses in the best way possible, how to decrease the thermal bridging and make the overall building with a super high energy efficiency standard, and how to better integrate the MEP in the walls. As said, we were cutting the wall outlets after the prints were done, which could have been dealt with in a many other ways. So I hope you find better ones. And of course, the BIM integration, which is, I think, one of the main things to really fully industrialize the printing process, or how to incorporate it, to bring it to the public, to bring it into mass use. Yeah, so this is the end of the presentation. Here's just another outlook that I'm showing you here that we're working on right now. We're scanning to print. So in this case, you see a test sample of a printed element that fits a bedrock that was scanned previously, and we used this data to print specimen formwork. Yeah, this is just to spark your ideas. Mihaela, this basically is the end of my presentation.
Thank you very much, Tim, for your insights and sharing your experience with us. Guys, don't hesitate to ask questions. Let's benefit from Tim's presence with us this morning. So maybe just, as a first question from my side, it will be, in the end, what are, let's say, the most important advantages you see in using 3D printing technology, and what you think it really bring to the construction industry?
There are many advantages I see. So there's the form freedom, and there's also the productivity and actually cost reduction when it comes to form freedom. So the formwork costs can be drastically reduced. All the manual labor that goes into building formwork that can be used only one time. I'm not talking about straight walls where they have great formwork systems that can be reused many times. Talking about formwork that is either built manually with wood, or formwork that is CNC milled. And yeah, we can just get rid of this, avoid this whole step, and we go from another advantage is staying digital. As I said, there is not much paper that was printed during this project.
Yeah. We have a question now. So thank you very much for this presentation. Is there an interest or a possibility to print pieces integrating your two materials, 1K and 2K, together in order to integrate complex shapes in the heart of simpler elements? For example, to make a reservation for electric cable or reinforcement?
Yes, we've been thinking about it. Before we actually started this house build, we're supposed to print a bigger house, especially on this grounds where you see this scan print right now. And therefore, we wanted to use exactly that. We wanted to have a material that is more robust or also a little cheaper for the mass. And we wanted to have the 2K material for the intricate shapes that are, to have a more appealing or even more appealing look. So we've been thinking about it, doing it like this, but we haven't combined it as such.
Okay, thank you. Another question. So thank you for the inspiring presentation and for sharing your failures as well. I'm wondering, how do you source your material? Also, have you experienced printing multiple materials in one print?
Okay, so the second question is basically that we haven't really incorporated two materials or two different style materials in one print. And the first question is a really interesting one, and this is hopefully something that can be solved very soon, because sourcing the materials is difficult, or actually the sourcing itself is not difficult, but the logistics behind it. Those materials are not produced everywhere, and this is a problem. So material is shipped around quite a bit right now, and I hope material manufacturers will broaden the production once the technology is more widespread. So it's basically goes together. The more 3D printers are around, the higher the demand for the printing mortars, the more material will be needed, and then I think the material manufacturers will spread the production all over the globe, or as local as possible. But definitely a very interesting point still.
Thank you, Tim. So did you experience problems of hydrostatic pressure when filling the columns with reinforced concrete, like the Lost formworks resisted?
We had those issues, but only in the before. We did quite some tests on that. And with the self-compacting concrete, it was no problem.
Okay, thank you. And the last question, what are the cure conditions and how much cure time before transporting the elements?
That depends. It depends if you're printing on platforms and move the platforms themselves, so you can move the items relatively quick after a couple of hours maybe, depending on the printing mortar as well. For those really big elements, we waited for a couple of days. I think the earliest we transported those elements was after 3 days. And the very big ones we waited for 7 days. All the printed items we covered right after printing with the tarps to prevent evaporation, to have a proper curing and hydration of the mortars itself. And the ambient room temperature was also, it was roughly around 20 degrees in the factory, but also humidity was quite changing. It's the properties on a lakeside in a relatively dry area, so it's mixed conditions as well, and we have big gates. So this has to be controlled with the sprinklers or spraying on the parts at some times. Yeah.
Okay, thank you very much, Tim. Thank you again for sharing with us your experience. Happy to have you here. And for all of you guys, stay tuned for the next webinar. Thank you very much to everyone.
Thank you very much for having us.
Thank you, Tim.